Okay, so sticking with stoichiometry, going to make it maybe a little more difficult. We're going to talk about a limiting reactant. So sometimes when we have a chemical reaction, we're limited on how much product we can make because we have a limited resource of reactant. That's why the stoichiometry, the multiple ratios are so important. Let's kind of go back to the whole pizza thing. So let's say again, I have my reaction here of making a pizza. I need 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese to make 1 pizza. Well, let's say, for example, I have 1 crust, I have 5 ounces of tomato sauce, but I only have 1 cup of cheese. Am I able to make the pizza? I'm not. And the reason being is because I would be limited on my cheese, so I couldn't make the full pizza. All right, so let's look here. Let's look at this problem. Let's say I have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce. How many pizzas can I make? Well, let's look at it individually. Let's look at that 4 crusts. So if I take what I'm given, 4 crusts, multiply it by the ratio of 1 crust to 1 pizza, I can make 4 pizzas. Okay. Now let's look at the cheese. If I have 10 cups of cheese, and how many pizzas can I make? Well, there's 2 cups of cheese to every pizza, so I can make 5 pizzas. All right, let's look at the tomato sauce. If I have 15 ounces, for every 5 I can make 1. So I have 15 ounces of tomato sauce. I have that ratio of 1 to 5, so I could make 3 pizzas. So if I have all of this, the most pizzas I can make is 3. And that's because I'm limited by the tomato sauce. So the tomato sauce in this case is what we call our limiting reactant. It limits how much product we can make. Picture version of that is here. So you can see that I'm limited with my tomato sauce. So using this same analogy, we can take that into our normal reactions and doing like we've just done with the stoichiometry. Okay, one thing I want to talk about is this word, theoretical yield. So yes, the tomato sauce is my limiting reactant, and it tells me how much product I can form. So the theoretical yield is theoretically how many pizzas I can form. And I get that based on the reactions that we just calculated. Okay, so the limiting reactant is the reactant that makes the least amount of product. Okay? The theoretical yield is the max number of product that can be made based on that limiting reactant. Sometimes though, if we're going into a lab or we're going to the pizza parlor to make the pizzas, we know that we can make 3 pizzas, right? Based on what we were just given. But let's say we burn 1, so now we've not made it. We actually only made 2. That's actually what we call an actual yield. So when you go in to actually do it, and it's different than whatever you get out of it hands-on, that would be your actual yield. Then we are going to calculate something called the percent yield. The percent yield is the actual yield divided by the theoretical yield. So it tells us what percentage that we made based on how much we could make. Okay, so percent yield, actual yield divided by theoretical yield times 100. Okay, so I encourage you to write this down as we go through this problem. So here we're making ammonia from nitrogen gas and hydrogen gas, right? Now, if a flask contains a mixture of reactants represented by the image on the right, so here it is. We have 2 nitrogens. So let's go ahead and write that. We have 2 nitrogens. And then how many hydrogens do I have? I have 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. Which image below best represents the mixture in the flask after the reactants have reacted as completely as possible? What is the limiting reactant and which reactant is in excess? So which do I still have left over? Okay, well, let's look here. If I have 2 moles of nitrogen, how many moles of ammonia can I make? Well, I look at the ratio here, 1 mole of nitrogen to 2 moles of ammonia. So I'm actually just going to calculate that. So I have 1 mole of nitrogen and 2 moles of ammonia. So if I do that math, 2 times 2 divided by 1. So if all my nitrogen reacts, I can make 4 moles of ammonia. Look at the same thing here for hydrogen. For every 3 moles of hydrogen, I make 2 moles of ammonia. So 3 moles of hydrogen, 2 moles of ammonia. Okay, so if all 8 moles of hydrogen react, then how much ammonia can I make? Well, you have 8 times 2 is 16 divided by 3, so that's a little over 5. So 5.3 moles of ammonia. Okay, so here, now we can look. Which one of these two limits how much ammonia we can make? It's this one. So if all 2 of my nitrogens react, then I should have 4 of these. Okay? 4 ammonias. The 4 is going to be my theoretical yield of ammonia. The nitrogen is going to be my limiting reactant because it yields the least amount of product. Where hydrogen would give us more, so that means that I'm going to have some hydrogen left over. Now, I can look at this. So here I'm going to find which one of these has 4 moles of ammonia. 1, 2, 3, 4, this one does, but so does this one. And we know that we're going to have some hydrogen left over because it's not all going to react. And it's showing here that I have 2 left over, and I can actually check that. So if the 2 moles of nitrogen react, how much hydrogen also reacted? So I'm going to use this ratio, 1 to 3. So 1 mole here of nitrogen, and then the 3 moles of hydrogen. So if the 2 moles of nitrogen reacted, that means 6 moles of hydrogen also reacted. I started with 8, so there's 2 left over. So this would be our answer. Hydrogen would be in excess, and nitrogen would be our limiting reactant. All right, so summarizing. Limiting reactant is the one that limits how much product we can make. The reactant in excess is one that we have left over. The theoretical yield is how much product we're going to make based on the limiting reactant. The actual yield is actually how much was produced, so that's done in the lab. I mean, you'll have to be given the information. And then the percent yield. Okay, so let's use it. Let's look at this problem here. Now, one thing is, how do you know you have a limiting reactant problem? You know it because you're given an amount of both your reactants, or 2 of your reactants. So I'm given an amount of this and this, and asked to find the theoretical yield of ammonia. So asked to find how much ammonia is made or how much product is made. Now we're going to do this as simple as we did the stoichiometry problems. We're just going to do it twice. We're going to do it for nitrogen monoxide, and we're going to do it for hydrogen, and see which one gives us the least amount of ammonia. Okay. So here is going to be our strategy. So we're going to do it twice. We're going to take our grams of nitrogen monoxide and we're going to find grams of ammonia. We're going to take our grams of hydrogen and we're going to find grams of ammonia. Whichever one of these gives us the least amount of ammonia, that's going to be our limiting reactant, and that will give us our theoretical yield. So grams to moles, molar mass, moles to moles, stoichiometry, the coefficients, moles to grams, and then we'll have our ammonia. All right. Okay, so let's do it. Here we're taking the grams of nitrogen monoxide, and we go to moles of ammonia. So this actually is just taking this to moles at the moment. So if I react my 86.3 grams of nitrogen monoxide, I'm going to form 3 moles of ammonia. If I react to 25.6 grams of hydrogen, I'm going to make 5 moles of ammonia. You can look at your moles here. Which one's the least? The least is coming from the nitrogen monoxide. So the nitrogen monoxide is going to be my limiting reactant. Then how much product I make, well, I make this many moles of ammonia, but then I can just go ahead and convert it to grams. So this would be my theoretical yield. So the answer would be 49 grams of ammonia. Okay. Let's do another one. All right, here I have titanium oxide reacting with carbon to give titanium and carbon monoxide. All right, so when 28.6 kilograms of carbon reacts with 88.2 grams of titanium oxide. Okay, so I'm given an amount for each one of these. So I know it's a limiting reactant problem. It tells me that 42 kilograms of titanium is produced. So that reaction is yielding this much titanium. This is our actual yield of titanium. It's telling us how much actually was produced. All right, I want to find the limiting reactant, the theoretical yield, and then the percent yield. So what we're going to do, we're basing it off looking for titanium. We're going to do exactly what we just did. We're going to take the carbon and figure out how much titanium is made, then the titanium oxide, figure out the titanium, whichever one is the least is going to be our limiting reactant, and from there we'll get our theoretical yield, and then we can calculate the percent yield. All right, so let's go to our strategy. All right, so we're going to take our carbon. We're given kilograms, we've got to go to grams first, and then grams to moles, moles to titanium. We're going to do the same thing with the titanium oxide. Whichever one of these is the least amount, then that will determine our limiting reactant. And then from there, we can convert it to kilograms and get our theoretical yield. All right, so let's do it. Here, if I set this up, you have 26 kilograms of carbon, go to grams, go to moles, go to the moles of titanium. You're left with 1.2 times 10 to the third moles of titanium. Do the same thing with the titanium oxide. You get to 1.1 moles of titanium oxide. So the titanium oxide gave us the least amount of titanium. Okay, everybody see that? So that means that the titanium oxide is our limiting reactant, and that this is how many moles of titanium is theoretically made. Now it's asking for the theoretical yield in kilograms, so we're going to convert that moles to grams to kilograms. So this would be the theoretical yield based on our limiting reactant. Now to find the percent yield, we're just going to take the actual yield that's given to us in the problem, 42.8. This should be kilograms, sorry, that's a mistake. Divided by the theoretical yield that you just found, 52.9. multiply it by 100, and that means that you made 81% of what you should have made. All right, let's see. We are now going to look at how we find the reactant that's in excess, so calculating how much is left over. So we're going to use that same example we just used. So keep that in mind. So we're adding another step to it, and that is calculate the mass of the reactant in excess. Well, we found out that this was our limiting reactant. So the carbon is our reactant in excess. So to find how much of the carbon is left over, we're going to use our limiting reactant. Our limiting reactant, which is the 88.2 kilograms of titanium oxide, if all that reacted, we can calculate how much carbon also reacted simply by using their ratios. So we're going to go from the limiting reactant, which is our titanium oxide, to find out how much carbon. So we're just doing the same thing. We're just using the limiting reactant to figure out how much of the other reactant was used. Okay, so here we go. We're going to start with how much titanium oxide we started with, because we know it's all going to get used up. Convert it kilograms to grams. Use the molar mass to go to moles. Use the stoichiometric relationship or the coefficients for the balanced equation to go to the moles of carbon. Then I can go from moles of carbon to grams of carbon using the molar mass, and then to kilograms. So if all of my titanium oxide reacted, which we know it did because it's the limiting reactant, this is how much carbon also reacted. So if I started with this much carbon, this is how much reacted, I just subtract the two. So I have 2.1 kilograms of carbon left over. That would be my reactant in excess. Okay. All right. A couple different types of type of reaction here is a combustion reaction. Combustion reactions are reactions that start with a compound that is carbon and hydrogen, or carbon, hydrogen, and oxygen. But here are the key components. Combustion means it's reacting with oxygen and is producing carbon dioxide, water, and heat. So this is the only thing that's changing in a combustion reaction, that and the stoichiometry. So if I want to write the combustion reaction for methanol, then I'm going to take methanol, react it with oxygen. Then my two products are going to be carbon dioxide and water. You don't really need to write the heat. Okay, that would be it unbalanced. Now I'm going to balance it. So I have one carbon, okay. I have 4 hydrogens, 2 hydrogens. So let's start there. So it'd be 4 and 4. I have 1 oxygen here, 2 here, so that's 3. But on this side I have 2 plus 2 is 4. This gives me an odd number, so I'm actually going to make a change here. I'm going to put a 2 here, so make it even. So I have 2 carbons now, so I'm going to put 2 carbons here. But now how many hydrogens do I have? I have 3 plus 1 is 4, times 2 is 8. So this is going to become a 4. 4 times 2 is 8. All right, so now 2 times 2 is 4, plus 4 is 8, so I have 8 oxygens. So I'm going to put I just did something wrong. I have 6 oxygens. So I'm going to do a 3 here. Sorry. This would be I have 8 oxygens on this side, but I have 2 here, so I need 6 here. So I'm left with my coefficients. So that would be the balanced combustion reaction for methane. Another type of standard chemical equation is our alkali metals. Our alkali metals react. They're group 1 metals. They form a positive 1 cation. You guys know this already. And their common reaction is this. The metal reacting with a halogen gives us an ionic compound of the metal and the halogen coming together. So like sodium reacting with chlorine gives us sodium chloride. These are generally very volatile reactions and very exothermic. All right, halogen overview. So halogens tend to react with metals to form ionic compounds, such as our metal and our halogen, which is called a metal haloid. Here, for example, I have my metal iron reacting with chlorine, gives me iron chloride. And then they also react with hydrogen to form what's called a hydrogen halide. So hydrogen with chloride would be HCl, for example. Okay. You actually don't need to worry about this. I'm not going to test you on writing the alkali metal and halogen reactions. You just need to be able to write the combustion reaction. It takes us to an end.